So yeah, basics of thermochronology is our focus now, and this will take us probably through to the coffee break, maybe a little bit more after that. So um, the general ideas for the course is essentially what we want to cover here, and that is what is the concept of a thermochronometer, what does it measure, and maybe how is it a bit different from traditional geochronology. Some of you probably already have some ideas about that. We'll also talk about the concept of a closure temperature and sort of what that means for thermochronology, and then talk a little bit at the end specifically about the benefits of low temperature thermochronology, so and kind of what that means in terms of temperature range and potential applications. Now, in terms of motivation, I mean, some of you have very direct motivation for being in the course already, that it might be part of your thesis research. But when it comes to studying modern orogens, thermochronology is probably one of the best methods we have available to measure things like long-term rates of rock exhumation. So this is things that take place over millions of year timescales, so much longer than things like if you're familiar with using cosmogenic radionuclides. They have a shorter timescale, or other methods you can use to measure erosion, like even sediment traps and things like that can measure erosion over sort of weeks to years timescales. But if you want really long-term average rates, you need something like thermochronology. And if you can study exhumation, you can then maybe relate that to rates of erosion or rates of tectonic activity. So the majority, I would say, of applications of thermochronology probably today are in studying modern orogenic systems. Not all applications, but I would say the majority. Another good portion of them are used in oil and gas industry. And the reason for this is, well, as you, again, may or may not know, maturation of hydrocarbons is essentially a temperature-dependent process. So in order to turn carbonaceous material into oil, you have to take it up to temperatures of something like 100 degrees C. If you take it beyond 100 degrees C significantly to about 200 degrees C, eventually all the oil is converted to gas. And if you continue cooking things up to about 300 degrees C, essentially all the gas starts to break down too, and you're left with something that can't be economically viable. So, as far as oil companies are concerned, we stop drilling here. But obviously, knowing the level of maturation, or sort of how hot things have been, is really important for finding oil and gas. Not only that, but it's also the fact that you can date when it was at those temperatures that's extremely valuable, because oftentimes structural traps that form, if you've got folds and thrusts that are bending the rock and trapping oil as it migrates, you want to know that the timing of the formation of those features is around the same time when the oil is being generated. Otherwise, you could produce your oil much earlier before things get folded, and the oil might just migrate away and not be trapped somewhere. So for the oil and gas industry, there's the apatite fission track thermochronometer has a closure temperature that is almost right in the sweet spot for maturation of oil, and it's been broadly applied in that industry as a result. And really, even some of the pioneering work in thermochronology, particularly going down boreholes, was done in the oil and gas industry. So, so it's an important thing that's still used today in those settings. Now here, for those of us that are living in Northern Europe, we're not in a modern orogen. We're not anywhere near an active plate boundary. But instead, we're in a sort of ancient shield setting, and thermochronology has not really been applied as broadly to these settings as it has to modern tectonic settings. And there's a few reasons for that, and maybe we'll get into them a little bit with what Ilmo's going to say. But there are potential applications. And so this is just one example of a study from 2006 in the sort of northern part of Canada, where they were looking at the rates of cooling and rates of exhumation of the Canadian Shield. And this was one of the first attempts to apply really low temperature thermochronometers. You can see some of the past studies here with like uranium lead dating and zircon, so you're up quite high temperatures, and then different methods that have been applied to get down lower and lower temperatures to eventually here in the range of maybe 50 to 70 degrees where the apatite uranium, thorium, helium system works. And essentially what they found is that the rates of shield erosion are extremely slow. If you average them out over the time scales we're looking at here, it's less than 2.5 microns per year. So it's remarkably slow. Now, I guess, if you look outside today, if you wander around, now that it's light out, if you wander around and you haven't seen the area here, you probably don't get the idea that it's rapidly eroding, and it's, of course, would be a similar situation here, that it's not. But these are areas where, there have been ice sheets and things like that may have affected the exposure of the bedrock, but still the rates on average of erosion are quite remarkably low. So then, to talk about the main distinction we can make here between geochronology and thermochronology, turns out this is not exactly a precise separation between two different things, but rather that in many cases you could think of geochronometers as essentially being thermochronometers. It just depends on what the daughter product is. If it's lead that's produced from the decay of uranium and thorium in a zircon crystal, the lead will diffuse, but it diffuses at such a low rate that essentially none of it's lost over geological time once you get below the temperatures at which the zircon crystals are growing. That's not sort of a hard and fast rule, but essentially, when we talk about geochronology, most people think about dating crystallization, dating formation of some rock as an absolute age. And I think it's mainly this interpretation that makes the difference in terms of what you think about. With thermochronology, often the ages are not linked to the formation of the rock or the age of the material, but rather the time since it cooled below some temperature. And that distinction is pretty important because the way in which you interpret your age data, of course, for geochronometers might be something to link it to the provenance of the bedrock units that are eroding, whereas the thermochronological ages might be a completely different thing and tell a very different story related to recent exhumation of those rocks. So this distinction sometimes can get a bit fuzzy, but this is our general idea, is that we're dating essentially two different things. Now, in terms of a definition for what we can call a thermochronometer, and basically I think this works for all the systems I can think of. We're talking about some kind of radioisotopic system, so it's going to be some radioactive parent isotope decaying. So we need a parent isotope that's radioactive. Most often this is uranium or thorium, but it can also be potassium isotopes, or even samarium can become important for certain minerals. So we got the parent, we got some daughter isotope or crystallographic feature. So depending on what you're looking at, if it's argon-based or helium-based systems, you have decay and you produce some kind of inert gas isotope that's trapped in the crystal. If it's fission track-based methods, you basically destroy the crystal lattice within some region where you have spontaneous fission and tear apart the bonds in the crystal lattice. And then you need, of course, the mineral where they're found. So we have some kind of picture of what's going on up here. The science for thermochronometry is basically just an analysis of this kind of thermochronometer data to understand thermal histories of rocks or of minerals. So this is more or less the interpretation of the data you can get from a thermochronometer, and that's probably not a big surprise. Just to make a distinction, people do, I don't know, in my experience, people use thermochronometry and thermochronology as essentially interchangeable. They're quite similar. If you care to have a different definition, you can say that thermochronology is the thermal history of a rock, mineral, or geological terrain. So it's not necessarily exclusively related to analyzing the data from thermochronometers, but rather just the thermal history itself. And as I've already kind of mentioned, most of the applications of thermochronology today are used to look at things like past tectonic activity or erosional processes and their rates over millions of years. And in order to do this, when we have these ages here, this kind of little inset plot here is just showing you time versus temperature. But what we have basically is a time since a given temperature. And in order to relate this to some kind of rate of tectonic movement or rock uplift or something like that, you have to then figure out what depth does that temperature correspond to in the Earth. And so we have to make the connection between the age and the temperature. And although this sounds easy and there are some simple ways to do it, this is really where the science is done today with thermochronology. There's certainly people that are working on improving the dating methods, but a lot of the focus is on interpretation of the data because that's really quite challenging. And that's, personally, that's where most of my experience lies, is using numerical models to interpret thermochronometer data rather than producing the data myself. I'm not really a laboratory kind of guy. So here we have kind of a nice picture, I would say, of the essence of thermochronology, and that is that we have some behavior in which the parent isotope, these gray balls, are converted to a daughter isotope in a closed system. So this little bottom of the hourglass is closed, and so when the daughter isotope is produced, it's trapped within the crystal. And in other cases, the behavior is different, where we have essentially an open system. Daughter isotopes are produced, but then they're lost by diffusion and not contained within the crystal. Of course, this radioactive decay is more or less a constant process. The amount of daughter product you produce depends on the concentration of the parent isotopes, but the sort of decay process is continuous. And the distinction between these two behaviors is on the basis of temperature. So when things are cold, we have basically the closed system behavior, and when it gets warm, we have an open system, and that's essentially what you can see here. So this it's a temperature-dependent diffusion process that really dictates whether that daughter isotope is trapped within the crystal or lost. And we'll see the age equation a little bit later, and you can kind of see how this age and the temperature are related to one another. And what we see if we look at the data in nature is that we don't have just sort of a binary switch from open to closed behavior. It's not like the door just slams shut at a certain temperature, but rather there's a gradual transition from having the daughter product lost to diffusion to being trapped within the crystal. In the zone over which this transition occurs, so here we're looking at depth versus apparent age. The depth range here, or temperature range here, is what's known as the partial retention or partial annealing zone. And as the name sort of alludes, that's the place where you're not retaining all the daughter product, but may retain some part of it, whereas down here at higher temperatures, the daughter product essentially is lost for geological purposes instantaneously. Now, of course, in human lifespans, there probably is still some measurable daughter product there, but over millions of years, that daughter product never has a chance to be retained in the crystal. And, well, there's just a little bit more of a definition of what the partial retention zone is there. So it's the point from where we retain all of the daughter product to the point where we're retaining none of it. That's the entire gray zone there. Now, I don't have so many questions in the lectures today, but I think I do like to try and pause every once in a while and give myself a break from talking and ask you some questions. So why do you think there's this partial retention zone? Why do we have a partial retention or partial annealing zone? So there's something I've already mentioned in terms of the process, and that's diffusion. Right? So we have these daughter isotopes trapped inside the crystal, and essentially they move by some kind of diffusion process. And at high temperatures, they diffuse out of the crystal more rapidly, and at low temperatures, they very slowly diffuse. Diffusion is driven mainly by concentration gradients. So outside of the crystal, there's no daughter product. That's always going to favor the daughter product moving toward the edge of the crystal, but the rate at which that happens will depend on the temperature. If it's very high temperature, it can quickly move from within the crystal out, and at low temperatures, essentially, it's trapped within the crystal. So this partial retention zone, partial annealing zone, is because that diffusion behavior, as the temperatures get warmer and warmer, the rate of diffusion goes up gradually. It doesn't go up and suddenly everything's diffused out and nothing is trapped within the crystal, but it gradually gets more and more rapid diffusion as temperature increases. And so as a result, some of the daughter product, for instance, if a daughter isotope is produced near the edge of the crystal within this zone here, it might be able to make it to the outside of the crystal as the rock is cooling. But if it's produced in the center of the crystal, it may not be able to diffuse far enough in the time before it's then kind of more or less permanently trapped. Normally, when we think about this stuff, we think about rocks that are sort of continuously cooling, so that the sort of diffusion gets slower and slower as the rock cools. Yeah.
The partial retention zone is the same when you have erosion rates of 1 meter by million years or 100 meters by million years?
Yeah. So no, it's not exactly the same. Yeah. And it's and we'll see an example of that. I think it's in this lecture in a little bit. But yeah, I mean, it's, if you think about it this way, when you have one of these isotopes trapped within the crystal, for diffusion processes, there's a characteristic length you can calculate, which is essentially how far it can diffuse in a certain time. And as you move through this, cooling more and more rapidly, the distance that one of those atoms could travel gets smaller and smaller. So as a result, this partial retention zone temperature range changes with the cooling rate. Yeah, that's a good question. So here we have this, and I think Claire said that you guys are going to play with this stuff tomorrow related to this closure temperature concept. But essentially, we can define this red dashed line here in the middle of the partial retention zone or partial annealing zone as our closure temperature. It's just a sort of useful reference point to say about what temperature does the system start retaining more daughter product than it's losing. And this was defined in a paper by Dodson in 1973. It's sort of probably the most famous thermochronology paper I think I know of, because it was such a simple concept that this meant you could easily calculate these kind of closure temperatures for different rock samples. The formal definition here is just it's a temperature of a thermochronometer system or thermochronological system at the time corresponding to its apparent age. Now, as a native English speaker, I've read that sentence many, many times, and it took me a long time to make sense of what it means. But essentially, the idea is that if you have the age of the rock, this is the temperature that corresponds to that age. So for an apatite fission track sample, it might be 110 degrees or something like that. It'll depend, of course, on the system. And it's an easy way to relate then ages to temperatures in the Earth, and then you take that step toward then being able to study rates of erosional processes. Now, the challenge here is that the closure temperature varies as a function of the mineral system you're using, so it's different for apatite, uranium, thorium, helium dating than fission track dating, than argon dating, etc. Of course, but it also varies with the size of the minerals, the chemistry of the crystals for certain systems, and the rate of cooling, as we've kind of already mentioned. And we also assume in this definition that the cooling is monotonic, so there's no reheating in the Dodson kind of method. We can simulate these processes with computers now, so it's not 1973 anymore. So if we want to have reheating, well, we don't use Dodson's approach. We just simulate the diffusion process directly, and by that we can then have samples that cool to the surface and get buried and re-exhumed, and get more complicated thermal histories out that way. So here's the plot where you can see a little bit about the cooling rates. And so what we have here on the horizontal axis is the rate of cooling. And these different little letters on here, you can only see a couple of them, are different thermochronometer systems. So this is helium within the apatite crystal. It's usually abbreviated AHE. And then down here at the bottom, kind of the higher temperature range, is argon in hornblende. And there's a couple things we can see here. Well, one is that as the cooling rate goes up, we see that this effective closure temperature also goes up. And this has to do with that partial annealing zone shifting. So as you cool more and more rapidly, these atoms can travel shorter distances to the edge of the crystal. So effectively, it means you're shifting to higher temperatures where you're diffusing out your daughter product. So in other words, yeah, this temperature just goes up. It's about a 40-degree change from 0.1 degrees C per million years to 100 degrees C for apatite helium. So you can see it's quite low temperature. So maybe 40 degrees C is a bit on the low end for very slow cooling, but it goes up almost by a factor of 2 for very rapid cooling. And the difference between this kind of minimum and maximum temperature is larger as you go to higher temperature systems. So for argon and hornblende, you'd start maybe, 470 degrees for very slow cooling, and you get to 600 degrees at the upper end for very rapid cooling. So anyway, that kind of this is just one example of one of these things that makes the data interpretation a little bit more complicated, this effect of the cooling rate. Because really what you want to do is try to study some kind of rate of rock exhumation from your age. But your age depends on the rate of rock exhumation, because that will affect the rate of cooling. So you have a sort of nonlinear problem here. And again, we have ways to deal with these things, but it's a little bit more complicated than it might seem at first blush. So yeah, I've got another question for you here, and that is, if we consider that the daughter product is diffusing out of the crystal, well, essentially, I guess we've already answered this question. And that is, why would the closure temperature increase for faster cooling rates? Well, I hadn't anticipated answering the question about the partial annealing zone when I made the slide, but we've basically covered this, right? That as you cool more and more rapidly, there's less time for diffusion to take place at a given temperature. So if you're cooling at an extremely slow rate, you're at higher temperatures for a longer amount of time, and so the isotopes, the daughter isotopes, can migrate a longer distance at that higher temperature. If you cool very quickly, you're only at those high temperatures for a short period of time, and so that change in the rate of cooling will reduce the distance that the daughter isotope can travel as it tries to migrate to the edge of the crystal. And as a result, then, this shifts the partial annealing zone to higher temperatures, and then, of course, the closure temperature would also go up with that. So I guess that's clear at this point. Yeah. So what we can do now is, just because I get bored lecturing, we can just make some simple calculation here. We know a few things now. So let's pretend that we can ignore the cooling rate effect for the moment for these following scenarios down here. The goal is to calculate the effective closure temperature, to use this effective closure temperature to calculate the ages of rocks for the following scenarios. We're assuming here that we're using an apatite uranium, thorium, helium thermochronometer, and we don't necessarily know exactly how that works yet, but it doesn't matter. But we know it has a closure temperature of about 75 degrees Celsius. So if we use that 75 degrees, and we have the following cooling histories that are all sort of 100 million years in total duration. We have one where we have rapid cooling from 500 to 15 degrees C at 40 million years ago. So extremely rapid cooling. Another where we have monotonic cooling, so just kind of gradual cooling from 135 to 15 degrees over 100 million years. A third scenario here where we're cool from 60 to 15 degrees 20 million years ago. And then you can read the other two. They're a little bit more complicated. What I'd like you to do is just to calculate what you would estimate the ages are for these different cooling scenarios. And I'll give you a hint for the first one here, that if we have extremely rapid cooling at 40 million years ago, what would we expect the age to be? And we can assume it's instantaneous cooling. So it goes from 500 to 15. We pass below the closure temperature at what time?
2 or 3 million years.
Yeah, right. I mean, we'll assume here that this happened, maybe this was right next to an intrusion or something like that, that the rock just intruded and cooled down from 500 to 15 degrees. We'll say, in this case, it would be 40 million years for the age you would get for the thermochronometer, because we're assuming here that the cooling is from 500 to 15 in just at that instant. Yeah. Now that's an extreme scenario geologically speaking, but what I'd like you to do then is to just estimate for the other situations what you think the age would be as you cool from 135 to 15 degrees, just continuously over 100 million years. So just as a straight line, linear cooling. And what I'd say with this is, this is also a good opportunity to maybe check with the person next to you and see if you agree about these scenarios, and if there are any kind of things that don't quite make sense about how to do this. We can also, that's a good thing to discuss with your neighbors. And so we'll take a few minutes to do that, and then we'll fill in a little. I have just an empty kind of spreadsheet thing on the next slide. We can fill in our ages there, and then we'll continue after that. So yeah, let's take a few minutes and work through these different scenarios. Okay, so let's take a look at what we have here. So I kind of gave you the answer already for this first scenario. That was the instantaneous cooling at 40 million years ago. We'll just go here. And in that case, I think if we cool from 500 degrees to 15 degrees at 40 million years ago, of course, we pass through 75 degrees at that same time. So we'd expect an age maybe of something like 40 million years. What about this scenario number 2, the monotonic cooling? And I just mean just kind of continuous linear cooling from 135 to 15 degrees over 100 million years. What'd you get for age in that case? 54? Anybody get anything same, different? About 60? Any other? 50? So we got somewhere between 50 and 60 so far. Is there any other number outside of that range? So the idea here is I just kind of started drawing this one on the board. essentially, if we start at 135 degrees and we want to pass through 75 degrees on our way to 15, that's the picture we have. And we're starting at 100 million years ago and going to 0. So essentially, what you want to do is just go straight across at 75 degrees and say, well, what's the time when it was 75 degrees? Here, the temperature difference is 120 degrees between the two. If you want to do it this way, I don't know, this is kind of how I tend to think about things. If you figure it's 120 degree difference in temperature, right? I'm not making any dumb math mistake. Over 100 million years, that means the cooling rate would be 1.5 or 1.2 degrees per million years, right? Yeah. So if we have 120 degrees over 100 million years, that's going to give us 1.2 degrees C per million years, yeah? So if you want, one easy way to do this is just to say, okay, well, I know that we've got to have 75 degrees as the sort of destination temperature. So the difference between 75 and 120 degrees, well, I guess you could use the difference between these two actually to get there. And so the difference between 135 and 75 is 60, yeah? So maybe you can already tell that that's going to be in the middle of the temperature range, so that gives you the 50 million years, yeah? So, you know, sometimes these things are a little bit, I don't know, maybe you kind of kick yourself once you're like, oh, right, this is, easier than you thought, but you know, it's also something where it is good just to go through the example. So we could say here that we'd expect something like 50 million years. We'll find out if we're right or wrong on the next slide because I have the answers there. So for scenario number 3, any guesses about the age there?
More than 20 million years ago.
Yeah. Yeah, it's going to be more than 20 million years. It's going to be more than 100 million years most likely because we don't know. Well, I guess if we assume that this is the only event that happened in the last 100 million years, we never get hotter than 75 degrees C. So we wouldn't have any record of cooling below 75 degrees C. So in fact, this is a little bit of a trick because if we're just assuming we were at 60 degrees and cooled to 15 degrees, well, we're below the closure temperature the whole time. We don't have any record. So we'll just put that in as a kind of blank line. What about this picture here for number 4? Did you get any kind of numbers for that one? Or did you not get this far?
You have just information on the slowing cooling, and you can't have information on isothermal condition because it's 60 degrees, and you haven't information on the slowing cooling because it's less than 75 degrees.
Yeah. Yeah, so we don't know anything about what happened in the last 75 million years. We would have something here, right, that we cooled from 100 to 60 degrees. So along the way, if we cooled over 25 million years, again, this is a 40 degree change in temperature over 25 million years. You can figure out the cooling rate from that. I don't remember what this works out to. Did anybody actually get a number for this one? It's like something around 80 some million years ago. It's yeah, well, we'll see on the next slide. I can't remember what the number is here. And what about this last scenario? Anything, can we, well, will we get an age here? Or a meaningful age, I guess. Yeah. Yeah. So again, the point here is to say that we have to have ideas of what are the limitations in terms of what we can say about our ages. If our samples don't go above the closure temperature, then we really can't say anything about what happened during that time period. Now, that's perhaps a little bit of an oversimplified picture because, of course, if we dip into the partial retention zone, we might lose some daughter product. Here, in this example, we're just assuming that the only thing that matters is the closure temperature itself. But the partial retention zone, you will start to lose daughter product, and so nature's a little bit more complicated. But again, the idea is that we wouldn't necessarily expect to get anything meaningful here. Now, as it turns out, what's actually quite interesting is, here we have our 50 million year age. It's about 85 million years for scenario number 4. If you use a simple numerical model of cooling for all of these different scenarios, they actually all come out to be almost exactly 40 million years. Now, this does account for this closure temperature part of the story. So it just happens to be a coincidence that all of these scenarios were taken from a textbook where they walk through, how you have to be careful in interpreting your data. So this, slow cooling, because of the effect of loss of isotopes in the partial retention zone, you actually end up with a slightly younger age than you might expect just based on the closure temperature alone. And for this scenario where we, didn't really reach the closure temperature, we would have gone into the partial retention zone and would have been losing daughter product in that time. So you would have less than 100 million year old age because you've lost some of the isotopes in the partial retention zone. So the point here is that when we deal with this data, there's a tendency to look at the ages and say, like, okay, that's the age. I'm just going to take my model and try and reproduce that age. But it is a little bit more complicated than that, and we'll see. I think the people that will talk to us in the next 3 days are much more qualified than I am to talk about the actual complexity of looking at the ages and interpreting them in detail, because they're working on how those ages are produced, and I'm very much looking forward to seeing what they have to say about that. So I think now is a good time maybe to pause and get some caffeine and things like that. So let's continue now and talk a little bit about what causes cooling. And that's kind of a critical thing for understanding thermochronology, is we need to understand cooling of minerals and what causes that cooling. And this is where we get to the erosion, exhumation, and uplift oh my slide, because terminology gets a little bit confusing here, and I fully appreciate that, as non-native English speakers, maybe some of these words just don't, you don't have any picture in your head of how they compare to one another. It's just as bad for people who are native English speakers that erosion and exhumation are often used interchangeably, and they do actually have definitions that are different. So I put them on here mainly just so that you know how they should properly be used. In practice, people are a little bit sloppy. We need a few definitions. So when we talk about exhumation, we're talking about, I don't really like this word, but I took this definition from another article, the unroofing history of a rock. So we're talking about removal of rock from above, and as caused by tectonic or surface processes. So this could be erosion by some river or glacier removing the rock above some other reference point, or tectonic exhumation can occur as well in extensional settings where just the motion of the two sides of a fault results in rock being removed from above. Erosion and denudation are a little bit similar. In fact, all three of these terms are similar, which is why they're often used in place of one another. But when we talk about erosion, we're talking about surface removal of mass at a spatial point in the landscape by both mechanical and chemical processes. So what that means essentially is, there we're focused more on things like weathering and physical and chemical weathering, erosion by landslides, by river incision, glacial transport, whatever. And denudation is basically just a more general term for removal of rock at a specific point at or under the Earth's surface. And so, again, these three things are not so different. When we talk about exhumation, the main distinction is that we're talking about rock being brought from depth to the surface. When we talk about erosion, we're normally talking about a process happening at the surface. And the subtle differences between the two, I wouldn't worry about too much right now. It's mainly just that you have the definitions now and you can refer to them if you need to. So I don't need to sort of belabor that. Another sort of term that's worth defining just a little bit is uplift, because of course there are different types of uplift that can occur, and there's kind of a famous paper from 1990 by Peter Molnar and Phil England, where they distinguish between rock uplift and surface uplift. And these things relate to exhumation, so it's worthwhile to make note of them. Rock uplift is basically just the vertical movement of rock relative to sea level. So this doesn't have anything to do necessarily with what happens at the surface. We're just talking about rock moving from some point vertically upward toward the surface with respect to sea level as the reference. Surface uplift, rather, is uplift of the Earth's surface then relative to sea level. So you might think these two things are one and the same, but of course, if you have rock uplift and surface uplift that happen at the same rate, those two things can both move up, but you have no exhumation. And when you start changing the rate of surface movement relative to the rate of rock uplift, then you start to get exhumation here. So basically, it's just that exhumation is the difference between the rate of rock and surface uplift. So if the surface is going up faster than the rocks at some depth beneath it, that means you must have some sediment filling in a basin or something like that. What's more common in thermochronology is to think about cases where the Earth's surface is not moving up as fast as the rock beneath it. So in other words, there's some kind of erosional process that's keeping the Earth's surface at some fixed elevation, and the rock beneath it is being moved up toward the surface as a result. And you can come up with very simple equations for how that stuff relates to exhumation. When we talk about exhumation, in most cases for thermochronology, we talk about erosional exhumation. So here we have maybe the geophysicist picture of mountains. So this is some block of the crust with some topography. We've got a valley here that might have a river or glacier in it, and we have things like hill slope processes, landsliding, and other things that happen on the hill slopes that are moving sediment around. Erosional exhumation, as the name would suggest, is when we have rock exhumed by the action of erosional processes, and this can kind of take place in any tectonic setting, and like I said, it's the most common type of cooling for thermochronology. So basically, by the action of these erosional processes, you're taking bedrock at the surface and moving it away, and essentially you could think about it as lowering the surface, or if the Earth's surface is kind of at a fixed elevation for some reason you want to think about it that way, what you would see is that there's rock being moved upward toward the surface as you remove the material above. So as rivers carve their valleys, the sense of motion of rocks relative to the Earth's surface is that they're going to be moving up toward the surface as the valley is being lowered down. And so for any given particle of rock here, essentially you're following some pathway that looks like this. The rivers are carving down into the landscape, and if you're in a tectonically active setting, you might have a thrust fault or something that's uplifting rock at the same time as rivers are carving down into the landscape, and you could have rocks then moving vertically upward from some depth toward the surface. And so this is in contrast to tectonic exhumation, which really only happens in extensional settings or in places where you have relative extension. Here, in this picture, you can see just by the movement of the fault alone that you're taking rock that was, if these two, this upper surface here was initially horizontal with the other surface in the hanging wall, the movement of the fault alone has exposed these rocks from where they were at depth to the surface. So there's not necessarily a requirement for any erosion, although if you have big extensional faults that uplift the surface, you also get erosion normally in those cases. So there's lots of nice extensional mountain ranges that are good examples where it's not like there's no rivers that form on that landscape. Of course, there's erosional exhumation there too. So this is just to distinguish between tectonic and erosional exhumation. There are other ways you can cool rocks as well if you have emplacement of igneous bodies or whatever, but we're not going to worry about that kind of stuff here too much. We're going to mainly focus on erosion and tectonic exhumation. So I mentioned earlier in the previous lecture this idea of the diffusion and how it relates to the thermochronometer ages. We'll get to that here, at least at part one of that here. So this is the age equation for radioactive decay. And so this allows you to calculate the age of some material as a function of the decay constant. So this is related to the half-life, but it's not the half-life. But that's basically a parameter that would be known for the isotope that's decaying. And then the ratio of the daughter product to the parent isotope. If you combine these things, you can measure the daughter product, we can measure the parent isotope. If we know the decay constant, we can find the age. So, we can have various ways in which we can measure daughter and parent isotopes, and decay constants are known for most common radioactive parent isotopes. And so in normal geochronology, this is what you would do to find the uranium-lead age, for instance, where lead would be the daughter isotope and uranium would be the parent. So that's how things work for general radioactive decay. But when we talk about thermochronology, we have to remember that we're dealing with a system in which the daughter isotope is not necessarily always trapped and continuously accumulating within the crystal, but rather it might be able to migrate. So here we have the diffusion equation that's used typically for modeling this kind of behavior. And here's the kind of picture if you want to look inside the crystal, at least my kind of silly picture of what it looks like, where you have some kind of parent isotopes here shown in red that have taken a place of a normal atom in the crystal lattice. So this is meant to be, some regular arrangement of atoms in some kind of very simple kind of grid-like crystal lattice. So, this could be silicon and oxygen and potassium or whatever, whatever mineral you want to have here. But in some places you've substituted in these parent isotopes that could be uranium or thorium or whatever. And when they decay, they produce these small little green guys that are daughter isotopes that don't go into the crystal lattice, but just get trapped rather within the crystal lattice. And so they're free to diffuse out of the crystal lattice. This is the equation that governs that diffusion. It's just a standard diffusion equation. So here we have the change in the daughter isotope concentration with time. So dNd, so Nd is the daughter isotope concentration for time. It's equal to some diffusivity that will depend on temperature for our cases, and then times the curvature or the second derivative of the daughter concentration with respect to the spatial coordinate here, x, plus some rate of production. So we're producing here, and this is where we're transporting or diffusing the daughter isotope, and then that combination determines how much the daughter isotope concentration increases or decreases with time. And the temperature dependence in terms of that diffusivity is just shown here. These equations, I think you will come back to playing with tomorrow. So I'm not going to worry about going into detail here because I think you'll be able to put this stuff into an Excel spreadsheet and play around. At least as far as I know from the lecturer tomorrow. But essentially you can see here that we have some diffusivity. Here it's divided by the diffusion domain. That's just the length scale over which the diffusion occurs. So that's basically some measure of the size of the crystal. And you have some diffusivity at infinite temperature. You can calculate that from diffusion experiments. There's an activation energy, which also you can get that way. Gas constant, and then here is temperature. So you have this e to the minus 1 over t behavior that gives you that diffusivity that goes up as temperature goes up. So yeah, or sorry, I think that maybe I said that backwards. But essentially it gets easier to diffuse as temperature goes up. And again, you'll come back to playing with that tomorrow, so I'm not going to say much more about that. We have just one other depiction here, or one other kind of picture of this idea of the closure temperature. I think it's shown kind of somewhat nicely in this image here, where here you can see temperature increasing along the vertical axis and time along the horizontal axis. And this is some kind of cooling pathway of some rock as it's coming toward the surface. And it'll pass first through this TO, which is the open system temperature. We can think of that as the temperature where all of the daughter product is lost and none of it is retained. Then through TC, which we've already talked about a little bit, where we have this Dodson closure temperature thing, again, that you'll play with tomorrow. And then finally onto TB, which is the blocking temperature, where now the system is fully closed. So any temperature below that, nothing gets out over geological time. Here is just showing you the ratio of the daughter product to the parent isotope. So above TO, or that's the time corresponding to this temperature, there's no daughter product accumulating because it's all diffused away. So that ratio of daughter to parent is 0. And then as time goes on, you sort of have this region where the amount of daughter product is increasing until you hit TB, and then it's basically just a straight line from that point, because as decay occurs, now all of the daughter product is trapped, and so you expect some kind of continuous increase in the ratio of daughter to parent isotopes. Again, I have some other things that I think we can talk about, so if there are questions, I'd be happy to answer them, but otherwise I'm also happy to move on to things that might be a little bit more exciting than plot after plot of basic theory. So we already talked about the Dodson equation, and you guys will play with that tomorrow. So I'm not going to worry about that for right now. What we can talk about, though, is why are we interested in low temperature thermochronology. So we've been just talking about thermochronology in general so far, not really why we care about low temperatures or what that low temperature means. And here, arbitrarily, we're saying 300 degrees or less on average. That's not quite a clean cutoff, because some people would put argon in muscovite, which is around 350 degrees. Some people would include that as a low temperature thermochronometer. But here's the picture: different mineral systems and their effective closure temperatures for argon-based, helium-based, and fission track systems. So over here on the left side are the systems that are below 300 degrees C. So for fission tracks, that's going to be apatite and zircon. Those are also probably among the more well-developed methods. For helium-based systems, it's apatite, and zircon is probably the second most heavily used, as well as titanite. and potassium, feldspar, biotite, and muscovite. I would include those as low temperature thermochronometers, although they're getting a little bit higher temperature, obviously. But you can see, tomorrow we'll hear about argon-based systems. Wednesday we'll hear about fission track, and then we'll hear about uranium, thorium, helium on Thursday. And I think we'll hear about each one of these different chronometers, different mineral systems when we do. But yeah, why is low temperature thermochronology useful? What do you think? Do you have any ideas why what would be useful about low temperatures? What can we do with low temperature ages that we couldn't do with higher temperature systems? Is there anything that comes to your mind? Maybe another way to think about this is, are there some things that might affect low temperatures in the crust differently than higher temperatures in the crust that might pertain to regions you want to study with thermochronology? So the key thing, or one of the really important things about low temperature thermochronology, is that we're more sensitive to the shape of the Earth's surface, to topography, than we are for high temperature systems. And we'll see why that is in just a moment. But essentially, the idea is that the isotherms, these lines of temperature within the Earth, will be bent or deformed by the topography at low temperatures. If you think about taking that to an extreme example, at the Earth's surface, the temperature of the Earth, it does change a little bit with altitude, because if you go up higher into the atmosphere, it gets cooler. But that temperature is more or less fixed as a constant value, essentially, to the Earth's surface. As you go deeper and deeper, of course, it gets warmer, and you get further away from that temperature boundary, and those lines that are initially curved and bent by the topography start to flatten as you go to high temperatures. And we'll see some pictures of this in just a moment. This is just kind of a nice image showing how the mountains here cause the temperatures beneath the mountains to be bent and sort of follow that rough shape. At high temperatures, what we see is basically this. If this line here is some kind of fake topography, some kind of fake elevations of the Earth's surface, at sufficiently high temperatures, the lines of constant temperature are horizontal, and they're not bent by that topography at all. And so what that means is that as rocks travel from this reference temperature up to the surface, the difference in the age, if everything's moving at the same rate upward, the difference in age is going to be only a function of the difference in how far these rocks had to travel from this starting line here. So in other words, this is a short vector here, so you expect to have younger ages at low elevations down in the valleys, and this is a longer vector here. So up at the peaks, you expect the ages to be older. And we observe this. There's a lot of places where if you look at here some kind of fake set of ages versus elevation, you see the ages get older as you go to higher elevations. So this idea seems to be something that, it's not just a cartoon, but this is what we observe. With low temperature thermochronometers, what we see is that the shape of the closure temperature isotherm will be bent to follow the shape of the topography above. Not exactly, but it will be some kind of damped version of that topography. So here you can see, this peak is present, but it's not quite as high as the one at the Earth's surface. And so these lines that we had initially, these vectors that showed us rock traveling from this horizontal reference point up to the surface, will change a little bit in their length. So here the closure temperature isotherm is closer to the surface than it was before. So this vector gets a little bit shorter. Here in the valley, this vector is a little bit longer than it was before. And so the blue is just kind of showing you the difference in the length of those. And that will then change this relationship of the sample ages with elevation. Okay, I guess that probably makes sort of intuitive sense. What's really interesting is that what this means is you could potentially study past topographies, because if the Earth's surface changes in the time between when you pass through your closure temperature and the time that the sample makes it to the surface, you can actually then see that difference in the past topography. It would have affected the samples moving through the closure temperature, but then the topography changed. In this case, this is sort of a cartoon example, but what's interesting is you can actually get relationships between the sample age and elevation that go inverted from what is typically seen. So that can be an indication that the topography has changed significantly in the past. So again, here's just showing the kind of difference in the length of these vectors. We don't need to worry about this in detail for right now, but it's there are a few places where this kind of relationship between sample age and elevation is opposite of what you expect, and that can be a sign that the topography has evolved significantly, which is kind of interesting. So just to sort of summarize that stuff and give us now a little bit of time to move on to the next bit about talking about exhumation rates, I'm going to ask you a few questions, and hopefully you have some idea. How does thermochronology differ from geochronology? It's kind of a nasty question, actually, but what's different between the two? What's the kind of, when you interpret the data, what do you think of differently? Yeah, Lotta. Yeah. Yeah, so sometimes those things can be the same, right? If you have like a good example is some of the volcanic deposits that are used as standards for thermochronometer analysis. They're essentially deposited instantaneously and cool over geological time within a very short time period. Crystallization age and the thermochronometer ages in those are the same. If you had a big, massive pluton that's intruded somewhere, those two ages might not be the same, because the crystallization ages might record very high temperature cooling, and then it may take several million years for the pluton to cool down. So thermochronometers might record something different in that case. What about this closure temperature idea? What's a closure temperature? I'm sure you all have some idea in your head about what it means. Maybe it's harder to sort of to say what it means. But if I said that I had the age of some thermochronometer sample and it was 10 million years, it's been 10 million years since what? Yeah. Right? So, it's the time since it was at some temperature, and that temperature will depend on that mineral system. But that's essentially the idea for the closure temperature. It's the temperature at which the system transitions from being open to closed, in a simplification of how it really works in nature, because we know this partial annealing zone makes things more complicated. And I'll let you off the hook here with what kind of things we can study with low temperature thermochronology, because we'll talk about that in just a second here.